Okay, today I want to talk about two things, which at first might seem unrelated, but in the end turned out to be very closely tied together. So those two things are the well-ordering theorem, the well-ordering of the natural numbers, and the second thing is induction, which hopefully is at least somewhat familiar to everyone. But if not, at least I will go over what these two things are, and then we'll try to see the connections between them, and potentially in a future video we'll elucidate on some further topics. All right, but to start out, what is the well-ordering theorem? I'll just write it down. If I have a subset of the natural numbers, and this subset is not empty, then, let me write it this way, then S has a minimum element, is what I should say. So what this means is that there exists some element of S such that for any other element of S, let me call that S prime, this S is less than or equal to S prime. So that's just saying there's some element that's smaller than or equal to all the other elements of S. So like, quick examples, if I take the set of natural numbers that are at least 4, like 4 and 5 and 6 and 7 and 8, all those numbers, that's a non-empty set of naturals, and it has a minimum element. The smallest element of that set is 4. Okay, but hopefully it's easy to convince yourself that like really this would work in any example. Anytime you have a non-empty set of natural numbers, there must be a smallest element of that set. And the reason basically is that like you could first ask yourself, is 0 an element of that set? Well, if 0 is an element of that set, then it must be the minimum element, because there can't possibly be anything in the set that's smaller than 0, because every natural number is at least 0, maybe bigger. Okay, so if 0 is in the set, then that's the minimum, and if not, then we could ask ourselves, is 1 in the set? If 0 wasn't in the set, but 1 is, then 1 has to be the minimum element, because it can't be 0, and nothing can be both smaller than 1 and not equal to 0. So if 0 is not in there, then we ask ourselves, is 1 in there? And if 1's in there, then that has to be the minimum. And if 1's not in there, then we continue. We say, is 2 in there? And if 2's in there, then that has to be the minimum. And if 2's not in there, then we continue. We say, is 3 in there, etc. And the idea is that if S is a non-empty set, then eventually we're going to have to reach some element of S, right? Just pick any element of S you like because it's not empty. And eventually, by that number of steps, we will have come across at least one element of S. So therefore, at some point in this procedure, we will have found the minimum element of S. That's the idea of why the well-ordering theorem is true. Also, I wrote that down as definition when it really should be a theorem. I don't know what was up with that. Okay. This is the well-ordering theorem. There's a little dash there. Okay. That's the well-ordering theorem. That's all it says, is that every non-empty set of natural numbers has a minimum element. So hopefully that's somewhat believable. All right, thing number 2, and I'll call this the principle of mathematical induction. Okay, the principle of mathematical induction says, if P of n is a proposition that depends on a natural number n, then the following implication is true. So, if P of 0 is true, and whenever P of n is true, then P of n plus 1 is true, if I know both of these things, then I conclude that P of n is true for all n. So let me actually spell out okay, let me first say, what do I mean by a proposition that depends on a natural number n? So by that, let me just give some examples to hopefully explain what I mean. We could have something like P of n could be the proposition n is even. And in this case, p of 0 would be true, and p of 1 would be false, and p of 2 would be true, and p of 3 would be false. Okay. So that's an example. Another example would be something like p of n is all n by n. Let me just, to avoid technicalities, all n plus 1 by n plus 1 matrices with coefficients in the real numbers are invertible. Okay, this one is always false. So p of 0 says that all 1 by 1 matrices with coefficients in the real numbers are invertible. That's not true because I could just take the 0 matrix. And the same is true for p of 1. P of 1 is false because there's a 2 by 2 0 matrix that's not invertible. And p of 2 is false because there's a 3 by 3 0 matrix that's not invertible. So in this example, p of n is a different proposition that depends on a natural number. And it's false for all n. Okay. Let me give another example. P of n could be n squared plus n is even. In contrary to this is kind of the opposite of the previous example in that p of n in this case is always true. If I take any natural number at all and I plug in, and I take any natural number n and I write down what's n squared plus n, that number will always be even, no matter what n was. So p of n is always true in this case. P of 0 is true, and p of 1 is true, and p of 2 is true, and p of 3 is true, etc. Okay, so now that we've understood what a proposition that depends on a natural number is, let's try to understand this line here and elucidate that more. Okay, so let me rephrase that. Rephrased. What I want to say is, if p of 0 is true, and well, let me actually just spell this out in as many words as possible. If p of 0 is true, and for all natural numbers, p of n is true. No, sorry. That's not what I mean at all. And for all natural numbers, if p of n is true, then p of n plus 1 is true. So in other words, by this I just mean I can deduce the implication p of n implies p of n plus 1. That'd be like the shorthand way to write this. Then, for all natural numbers n, p of n is true. Okay, so this is the principle of mathematical induction. Okay, there we go. It just says that if I have any proposition which depends on a natural number, I can prove it by first proving what's called the base case, proving p of 0 is true, and then proving what's called the inductive step, proving that whenever p of n was true for some arbitrary n, then the next instance of p has to also be true. If I can deduce both of those things, then I'll know for all natural numbers n that p of n is true. And the idea here is that, like, okay, I've deduced that p of 0 is true, and if I've also deduced this property here, this inductive step, what that means is, by knowing p of 0 is true, I've satisfied p of 0, and so I can deduce p of 1 must be true. So that'll give me p of 1. And then for the same reason, once I know that p of 1 is true, I'll be able to deduce that p of 2 is true, etc. Okay, so this is the idea of, like, why the principle of mathematical induction should be true. All right, so we have these two ideas, the WellOrdering theorem, the principle of mathematical induction, and it's correct to say that these are provable things. You can prove the WellOrdering theorem, and you can prove the principle of mathematical induction, but to do so, we have to get into, like, the nitty-gritty details of the fundamentals of set theory, which I don't want to do in this video. So instead, what I want to say in this video is the following. Here's my claim for this video. The WellOrdering theorem is equivalent to the principle of mathematical induction. that, so what I mean by this is, if I knew ahead of time that the well-ordering theorem is true, then I could easily produce a proof of the principle of mathematical induction. And the second thing I want to say is that if I knew ahead of time that the principle of mathematical induction was true, then I can produce a proof of the well-ordering theorem. So that's my claim for today. And so I'm going to go prove those things now. Okay. So we need to do two things here. First of all, I want to prove that if the well-ordering theorem is true, then I can deduce the principle of mathematical induction. So that's my claim here. So I'm going to suppose that the well-ordering theorem holds. Okay. Now, the idea is, so I'm supposing that the well-ordering theorem holds, and now if I want to prove the principle of mathematical induction, let me look at the statement. What does the principle of mathematical induction say? Okay, it says if I have some property P, and P of 0 is true, and this inductive step holds, then P of n must be true for all n. So if I want to prove that the principle of mathematical induction is true, then what I should do is let P of n be a proposition that depends on the natural number n. And we're going to assume that P of 0 is true, and that for all natural numbers n, if P of n is true, then P of n plus 1 is true. Okay, now my goal is to prove the principle of mathematical induction, so that means what I should be doing here is supposing these two things, supposing P of 0 is true, and supposing this inductive step, and then deducing in the end that P of n is true for all n. Okay, so how am I going to do this? I'm actually going to do it by contradiction. I'm going to suppose for contradiction that the statement for all natural numbers n, P of n is true, that statement is false. Because that's the statement I want to deduce. I want to deduce the statement that for all natural numbers n, P of n is true. So I'm going to suppose for contradiction that that's false, and eventually I'm going to derive a contradiction. Okay, what would it mean for this statement to be false? What does it mean for the statement for all n and n, P of n is true to be false? What that means is that there has to exist some natural number n such that P of n is false, right? If there didn't exist any natural number n with that, such that P of n was false, then it would be the case that for all natural numbers n, P of n would be true. And conversely, if for all natural numbers n, P of n is true, then there does not exist a natural number n such that P of n is false. So saying that for all natural numbers n, P of n is true is false is the same as saying that there exists a natural number n such that P of n is false. Okay, and what that means is that the set, let's call this set S, set of natural numbers n, such that P of n is false, this set is non-empty. All right. So now, remember that I've supposed from the very beginning that the well-ordering theorem holds, because I'm trying to prove the equivalence of these two things. I started by supposing this is true, and I'm going to deduce by this that this is true. And then we'll go in the other direction. Okay, but I've supposed the well-ordering theorem holds, and remember what the well-ordering theorem tells me. The well-ordering theorem tells me that for all non-empty subsets of the natural numbers, I have a minimum element of that subset. Okay, so let's look at this example here. Here I have a non-empty subset of the natural numbers. This set of all natural numbers n, such that P of n is false, is non-empty because I knew that there had to exist some n such that P of n was false. So, by the well-ordering theorem, I conclude that S has a minimal element. Let me call it m. Okay. Now my goal is to show, is to derive a contradiction. So what this means that S has a minimal element m, hence P of m is false. Okay. So now, how am I gonna derive a contradiction here? Well, since m is the minimal element of the set S, we can think about the natural number m minus 1. Well, actually, let me take a step back here. First of all, m is not equal to 0, because by assumption, because by assumption, p of 0 is true. We had assumed that already. Okay, so if m is not equal to 0, then m minus 1 is also a natural number. So that's good news for us. I claim, since m was the minimum element of S, p of m minus 1 is true. And the reason for that is just that m had to be minimal. If p of m minus 1 wasn't true, if p of m minus 1 was false, then m minus 1 would have been an element of S. But that would have contradicted the minimality of m. M has to be the smallest element of S, and if m minus 1 was also an S, that would not be the case. So that tells us that p of m minus 1 has to be true. But now we look at our other assumption we made, the final remaining assumption, was this inductive assumption, that for all natural numbers n, if p of n is true, then p of n plus 1 is true. And so I'm just going to apply this in the case where n equals m. I'm going to say, since p of m minus 1 is true, then p of m has to be true. So let me write that down. Since p of m minus 1 implies p of m, that's a special case of our inductive assumption. We have p of m is true, but this contradicts the prior deduction that p of m is false. Alright, so that was a contradiction, which I'll denote with this little lightning bolt symbol. And what did we suppose for contradiction? Let's look. We supposed for contradiction that this statement was false. That for all natural numbers n, p of n is true, that statement was false. Okay, so of course, because we've now deduced a contradiction, that statement that we assumed was false actually must be true. So let me write that out. Therefore, the statement, for all natural numbers n, p of n is true, is true. And that's what we wanted to get in the end. We were trying to prove that the principle of mathematical induction holds in this case, so we started with the proposition of p of n, we assumed that p of 0 is true, and we assumed that whenever p of n was true, then p of n plus 1 is true. And from that, we used this argument to deduce that for all natural numbers n, p of n is true. Alright. So that was the proof that the WellOrdering theorem implies the principle of mathematical induction. Let's do the other direction. So in the other direction, I want to prove that if the principle of mathematical induction is true, then I can deduce the WellOrdering theorem. So what we're going to do first is assume the principle of mathematical induction is true. So assume the principle of mathematical induction is true. Okay. Now my goal here is to prove the WellOrdering theorem in this context. The WellOrdering theorem says something about every non-empty set, but before we get there, I'm actually going to take a little detour. This proof might seem like a little mysterious at first, but I promise we'll get to the correct conclusion in the end. I want to use my principle of mathematical induction to write an inductive proof of a particular claim. So let me just write that out. Let p of n be the proposition for all natural numbers k less than or equal to n, every subset of n which contains k has a minimum element. Okay, this might seem a bit complicated and unwieldy, It would be much simpler if we used strong induction to prove this, for example. But I'm not sure if everyone has heard of strong induction or knows what that is, so I wanted to maybe avoid that detail for now. And I've kind of wrapped up the proof of strong induction inside this argument here. In any case, I hope this is still like a somewhat understandable proposition. The proposition P of n says that for every natural number k which is not greater than n, so this is a natural number, that every subset of n which contains this particular natural number k must have a minimum element. So for example, the statement P of 1 says two things really. The statement P of 1 says first of all that every subset of n which contains 0 has a minimum element, and that every subset of n which contains 1 has a minimum element. So let's prove this. We're going to prove this by induction, of course. We're going to use our assumption that the principle of mathematical induction is true. And if we're going to do an inductive proof of something, we need two parts. We need the base case and we need the inductive step. So let me write out the base case. In the base case, I need to prove that P of 0 is true. And let me actually just explicitly spell out what is P of 0 in this case so that we can see why this is true. P of 0, just copying letter for letter, is going to be the statement that for all k less than or equal to 0, every subset of n which contains k has a minimum element. But of course, the only natural number which is less than or equal to 0 is 0 itself. So if this is going to be, if we're going to prove P of 0, well, I have to prove this for all k less than or equal to 0, but there's only one k to check. The only time I have to check this is when k equals 0. And so what I need to do to prove P of 0 is to prove that every subset of n which contains 0 has a minimum element. Well, why is that true? It's just because 0 has to be the minimum element of any such set. So let me write that. This is true because 0 is the minimum element of any subset of n which contains 0. Okay, why is that true? That's just because if 0 is an element of a subset of n, 0 has to be the smallest element of that subset because there's no such thing as a natural number which is smaller than 0. The natural numbers start at 0 and get bigger from there. Okay. So that wasn't too bad, base case pretty easy. The inductive step is going to be a little more involved, but really not too wild. We'll take it step by step. In the inductive step, remember, what I want to do here is suppose that P of n is true, and deduce that P of n plus 1 is true, right? I'm supposed to show in the inductive step that for all natural numbers little n, if P of n is true, then P of n plus 1 is true. So I need to choose an arbitrary little n, and then prove that if P of n holds, then P of n plus 1 holds. Let me write that. Let n in n be arbitrary, and suppose P of n holds. So this means that for all k less than or equal to n, I say it like this, for all subsets of n, if k is an element of S, then S has a minimum element. Right, that's just a rephrasing of what P of n says. P of n says that for all k less than or equal to n, every subset of n which contains little k has a minimum element. That's all we have there. All right, now I need to prove that P of n plus 1 is true. P of n plus 1 is the same statement where I just put an n plus 1 here instead of the n. And so if I'm going to prove a statement like that, I better choose an arbitrary k and prove it for that k. So to prove that P of n plus 1 is true, we're going to let k be arbitrary such that k is less than or equal to n plus 1. All right. Now I'm going to handle the rest of this in two cases. So case 1 is where not only was k less than or equal to n plus 1, case 1 is going to be where k was less than or equal to n. That's certainly some of the time. Well, what happens if k is less than or equal to n? Then I can actually just apply p of n, right? My assumption is that p of n is true, and p of n tells me that for all k less than or equal to n, I have that for all subsets that contains k, that subset is a minimum element, and that's exactly what I want to show in this case. So in this case, p of n applies to tell us that every subset of n which contains k has a minimum element. Okay, that's what we wanted to do, so that's good. We handled that case. All right, case 2. Case 2 is where k isn't less than or equal to n, but of course, still we need the assumption that k is less than or equal to n plus 1. So in this case, the only possibility is that k equals n plus 1. All right, now, in this situation, what I'm going to say is, if there exists some s, before we get there, I haven't said that. Okay, so in this situation, I want to prove that p of n plus 1 is true. And remember that p of n plus 1 is this statement here, but where I sub in an n plus 1 for this n. And now I'm focusing in on, I chose a particular k, chose this k, and this k turned out, in case 2, turns out k was actually n plus 1. So now what I'm trying to prove inside case 2 is this statement here, where this k is an n plus 1. So I'm trying to prove that every subset of n which contains n plus 1 has a minimum element, which I'll do now. If I want to prove that, I want to let S be a subset of n, such that n plus 1 is an element of S. Now, I want to show that S has a minimum element. And the way I'm going to do this is, I'm going to consider, again, kind of two cases. If there's some element of S such that S is smaller than n plus 1, then, of course, that element, little s, would have to be less than or equal to n. And as soon as that's true, as soon as big S contains an element that's less than or equal to n, then our inductive hypothesis will apply again. P of n will apply to tell us that S has a minimum element. Right? That's just because P of n tells me that for any k less than or equal to n, if S has the element k, then S has a minimum element. All right, and so in this case, if I find some element little s that's less than or equal to n, S must have a minimum element. All right, otherwise, if this wasn't true, if it's not the case that there exists some s such that S is less than or n plus 1, what must be true is that for all S in S, S is greater than or equal to n plus 1. And therefore, n plus 1 is the minimum element of S. So that's just saying, could there be a smaller element of S? No, because I already covered the case where S had any element smaller than n plus 1. And we know n plus 1 is in there. That was our assumption right here, that n plus 1 is in S. So we've assumed n plus 1 is in S. We covered the case where there was some smaller element. We covered the case where there was no smaller element. And therefore, any time n plus 1 is in S, S must have a minimum element. So either way here, we found that S has a minimum element. But then, because S is arbitrary, well, I won't even say that part. We did what we wanted here, right? We showed in each of these cases that any subset of n which contains k has a minimum element. And k was arbitrary, so I'll write that part. K was arbitrary. So P of n plus 1 holds. That's what we wanted to do to show P of n plus 1. I took an arbitrary k less than or equal to n plus 1, and then I wanted to show that every subset of n which contains k has a minimum element, which we did. All right. So P of n plus 1 holds. Knowing that, okay, that completes our inductive step. We assumed that P of n held, and we deduced that P of n plus 1 holds. and that was for any arbitrary n. So since little n was arbitrary, that completes the inductive step. All right, very good. So we did our base case, we did our inductive step. Now we know the principle of mathematical induction is true, and therefore we've deduced the statement P of n for all n. The principle of mathematical induction is exactly what lets us deduce that. It says if we've done the base case and the inductive step, then P of n has to be true for all n. So let me write that. By the principle of mathematical induction, P of n holds for all natural numbers n. Very nice. Okay. I still need to prove the well-ordering theorem, right? That was my goal all along. And I mentioned before, we're going to take a little bit of a detour. We finished the detour, we're back on track. We're now going to prove the well-ordering theorem. So, if I want to prove the well-ordering theorem, which says that every non-empty subset of n has a minimum element, what I need to do is pick an arbitrary non-empty subset of n and prove that it has a minimum element. So let's do that. Let S be a subset of n such that S is non-empty. Now, what this means, then there exists some element little s in S, right? Otherwise S would be empty. So there has to be at least one element. So let's call that little s. But remember that we know P of n holds for all n. So let me say now, because P of s holds, well, let me remind you what P of s says. For all k less than or equal to s, every subset of n which contains k has a minimum element. That's what P of s says. Now because this holds, we conclude immediately that S has a minimum element. That's all we have to do, because this statement P of S, it says something about all k less than or equal to S, but we care in particular about k equals S. If k equals S, we have right here a subset that contains k. We have this set S, this set capital S, which contains little s. And therefore, it must have a minimum element because P of little s is true. All right, so that proves the well-ordering theorem. Thus, the well-ordering theorem holds. And that was the second part of our proof. So I'll put a little QED box. Very nice. Okay, so to recap, what did we prove here? We proved this claim, that the well-ordering theorem is equivalent to the principle of mathematical induction. That should be an I. So that was our claim, that these two concepts, these two statements are equivalent. Proving either one is actually not trivial, and requires us to actually define what the natural numbers are, and it requires us to use all the axioms of set theory. It's a complicated thing to prove. Complicated to prove either one of these things. But maybe one of these seems more intuitively obvious than the other to you. Maybe to you it seems like, oh, the well-ordering theorem is obviously true. Every non-empty subset of n has to have a minimum element. Or maybe to you it seems like the principle of mathematical induction is obviously true, that if P of 0 is true and P of n implies P of n plus 1, then P of n always has to be true. That maybe that's obvious to you. So whichever one of these is more obvious to you, this claim at least should justify that the other one is also true, because they're completely equivalent properties. Hopefully both of these statements seem intuitively obvious to you, but if not, that's fine too. It's completely reasonable to be skeptical of these beliefs, to be skeptical of these claims until you've actually seen them proved. Until then, they're just kind of beliefs that have been forced upon you. So yeah, I won't prove those in this video. Maybe in a future video, but not for today. Okay, so I think I'll stop this video here, but I think in a follow-up video, I'll talk a little bit philosophically about why we even care about these two statements, how do we use these two statements, and I think those two topics will be the subject of a future video. All right, bye for now.